Hello, welcome to lecture 7. So in the previous lecture, we defined the total gravitational, we told that the total gravity, there's something called a total gravitational force. So total gravitational acceleration, this is combination of the, uh, the, the gravitational acceleration due to Earth's mass and this other term, which is the centrifugal acceleration that arises because the Earth is now rotating. So both of these terms act on a certain particle, certain element that is there on Earth's surface. The centrifugal term is of course important. It gives Earth the oblateness. So you know that we have done it in uh, advanced science that Earth is not perfectly a sphere. It has certain oblateness, and this is the centrifugal term is something that gives that oblateness. So if I draw an exaggerated version of that oblateness, this will look something like this. So this is the solid Earth, and then this is the spherical Earth, and this is something which is oblate. So this is of course very exaggerated. This is not how this is not to scale. This is not what exactly happens in um, the real Earth. There are the differences between the radius at the equator and the radius at the pole is very less as compared to the total radius of the Earth. Um, the However, I have exaggerated just to show you. So there is a particle of interest which is here, and then this is the capital R. This is the perpendicular distance from the axis of rotation. We have already defined this, and this is the gravitational acceleration. It's G, Newtonian gravity, just because the Earth has mass, so everything is being attracted towards the center of the Earth. Uh, the centrifugal acceleration at this point will try to push the element away from the surface. Um, so you can uh, of course feel it, for example, in a merry-go-round. If there are people going around, if you ride on a merry-go-round, you feel an outward force. So this is the centrifugal force, and most of us have done this in advanced science classes. So this effective gravity now, because now we have included small g and omega squared r, so there is an effective gravity which acts something in this direction, which is not exactly um, through the center of the Earth. So this is of course exaggerated, and this passes through the center of this oblate Earth, and this is called the G prime. And I'm of course exaggerating. This is not exactly to scale, and this surface that I have drawn is an equipotential surface. So this is the equipotential surface, or this is called the geoid. Already defined this. This is the geoid, so this is the equipotential surface. So this is the surface in which, if you leave the oceans to be, this is the surface, on which the oceans, the mean sea level of the ocean will lie on. So without any effects of tides and winds and other currents, other complications, we just let spherical Earth rotate. And if you do not include the impact of the atmosphere, this is how the mean sea surface would look like. So this is an equipotential surface. That is, there is no difference if you whether you are here or whether you are here. You are in the same potential. This is, this point A versus point B has no difference in potential. So G prime in this case is the effective gravity. It's the one due to the Earth's mass and one due to the centrifugal acceleration. So we'll drop the prime. So we'll, in all cases from now onwards, we'll assume that whenever we say G, this is the effective gravity. So we'll drop the primes from the next slide onwards. That is, so dropping the prime over G, that is G prime. So we write the momentum equation as so you can see now I have dropped the prime and there is no centrifugal acceleration here. There is only the Coriolis term, the Coriolis acceleration, that appears in this in the last term of this momentum, the modified momentum equation. This modification is because we want the Newtonian laws to be valid, and hence we have transformed our we have introduced new terms to account for the acceleration of the rotating frame of reference, or I mean acceleration of the frame of reference, that because our frame of reference is rotating. So that is the reason why this new term arises. This G is actually G prime. We have dropped the primes, as I said, we have dropped the primes, and this is equal to G prime, which is defined earlier. The G prime equal to G plus omega squared r. This is the effective gravity. So the omega squared r term, by relative magnitude, this is not a significant fraction of this capital G. You know the capital G is approximately 9.8 meters per second squared. This omega squared r terms, in whenever whatever maximum r you can imagine this to be, let's say the omega, the capital R is the radius of the Earth, the maximum, this omega squared r is approximately, the maximum value of omega squared r is approximately 0.5% of the acceleration due to gravity. So it's much lesser as compared to the acceleration due to gravity. So now this Coriolis term 2 omega cross u, or the omega cross u, you can see that this x perpendicularly, so this x perpendicular omega and u. So this x perpendicular to both omega, that is the axis of, which is along the axis of rotation, and the u velocity. So it deflects a fluid to the, so that I mean this omega cross u, so it deflects a fluid which is perpendicular to both omega and u. So it deflects a fluid element to its right on the northern hemisphere and to left on the southern hemisphere. It deflects a fluid to its right on the northern hemisphere and to the left on the southern hemisphere. So this has to be the case to conserve the angular momentum, because the Earth is rotating, and at different locations the distance from the center of distance from the axis of rotation is different, and hence they have different angular momentum, and without any external torque working on it, if there is change in latitude, there will be change in angular momentum, and hence there should be a deflection. And you can see that, I mean, you can we can calculate, we'll see again, I mean, in a slightly more simplified version, that this will deflect the element to its right in the northern hemisphere, because the angular velocity, the local angular velocity is now pointing upwards, pointing up out from the Earth's surface. So this Coriolis force is this Coriolis, I mean, it's the Coriolis term is called the Coriolis force. This is a fictitious force, so this is not something that actually exists, but this appears because now the frame of reference is rotating, so that is why it's called a fictitious force. So now let's examine, as I mentioned previously, so we want to see the effect of the Coriolis term in a more simplified form. So let's examine the motion of a free particle. So motion of a free particle on a plane. So this is not subjected to any force. So there is no force acting on this particle, and this is moving on a horizontal plane. So no external force is acting on the particle. Now the equations governing the motion is du by dt minus 2 omega v equal to 0. Now this is a particle. This, we are not talking about a fluid element here, so there is no concept of I mean, there is no external force acting on this. There is no frictional force, there is no viscosity, there is no pressure gradient, and this is just moving in a horizontal plane. And so du by dt is the x momentum equation, and dv by dt plus 2 omega u equal to 0. These are the x and the y momentum equation. So general solution, so the general solution to this system is u equal to a star sine ft plus c1, v equal to a star cos ft plus c1, where a star is some constant that I mean, it's just giving us the maximum amplitude here, and sine and cosine functions are, of course, you can derive it. You can see that this is a general solution to these equations of motion, the equations of motion that I have written here. The C1s are some constant, and F here is a parameter. It's a parameter of interest. This is 2 omega. There's a reason why we do this. This is, I mean, it has been called historically the Coriolis parameter. Okay, so this is just the 2 times the angular velocity of the rotating plane. So, okay, so there's a plane, and this is rotating at some angular velocity about this axis, and there's a particle in this. So this is the system that we are studying. So this is called the Coriolis parameter. Now to get the trajectory, integrate dx by dt equal to u and dy by dt equal to v. So perform these two integrations, so we'll get that x equal to x naught minus a star by f cos ft plus c1 y equal to y naught plus a star by f sin ft plus c1. So using both of these expressions x and y, we get, I mean, you can verify for yourself, we can x minus x naught the whole squared plus y minus y naught whole squared is equal to a star by f. And you will see that this will take a form which is slightly different in a spherical um, I mean in a rotating sphere. Here we are doing on a plane. I mean, please remember this. So we are doing a motion of a free particle on a plane, and we'll then move to a more general form, that is motion on a sphere. So here in this case, f is 2 omega. It's so here we get once we get the trajectory, we get a form of this which is like this, and you can pause it for a moment and say what is this trajectory, what does this trajectory look like. And if you recall, this is the trajectory of a circle, centered at x naught it's a circle centered at x naught comma y naught, and radius a star by f. Okay, so the motion of a free particle on a plane which is rotating at angular velocity omega is a motion described by this equation of a circle. And you can get the we have, I mean, the circle which is centered at x naught y naught, and the radius a star by f. Of course, x naught and y naught will depend on the initial time, and it is the initial position at the time t equal to 0. This is from where you start your calculations. So we define something called an inertial time period. So definition of an inertial time period, Ti is equal to 2 pi over f. This is the definition of an inertial time period. The description of, or the definition of f initially makes this things easier for us to define. So historically f has been called the Coriolis parameter, and this is called the inertial time period. And this is half the time period of the rotation of the plane on which the particle is moving. And the spontaneous circling of the free particle starting with an initial velocity is called the inertial oscillation. So free particle now which is moving in a rotating frame of moving in a rotating plane in the horizontal plane, and rotating about an axis which is perpendicular to the horizontal plane. So this particle will do the circular motions, and these oscillations are called the inertial oscillations. So for a sphere now, I mean, we have done it for a simple case. Now particles moving on a planar motion. For motion on a sphere, for motion on a sphere, so let's say we define we draw a sphere something like this. So we use a coordinate system where x is the direction in the east, y is the direction in the north, and z is the direction upwards. And this is the axis of rotation. The rate of rotation or the angular velocity is omega. So this is north and this is south. And this is the rotating, and this is the frame which is rotating along with Earth. This is fixed on the Earth's surface. That is, for example, we are standing here, and this is the frame of reference which is attached to the floor that we are standing on. So this is this is angle phi. So this is the angle which this point makes with the center, and this is of course the latitude. This is the latitude in which wherever you are taking your measurements from. So for flows smaller than the radius of the Earth, or much smaller than the radius of the Earth, so much smaller than the radius of the Earth, the curvature of the Earth is not important. The curvature of the Earth is not important, and we'll be dealing with such flows only because we have a Cartesian coordinate system. Otherwise, we would have to move to a curvilinear coordinate system, which will make our algebra slightly complicated. We are taking Cartesian coordinate system. We are assuming that the motion of the motions that we are dealing with are not significantly affected by the curvature on the Earth, and hence locally we can assume we can use a Cartesian coordinate system. So in this framework, this omega vector can be represented as omega cos phi j cap plus omega sin phi k cap. So j cap and k cap are along the z vector, the z and the x. So at each of these, sorry, z and the y. So this is the y direction, this is the z direction. So there is no component along the east direction. So x is the east direction. That is, if you have a sphere, or I mean, where you're standing, let's draw a line along the east direction. That is x. Let's draw a line along the floor, along towards the north direction. That is y. And and from the intersection of that x and y, the perpendicular line that is coming up is the z vector. And at each and every point, you will the omega vector is in the yz plane. So if you have a plane like this, the omega vector will lie always on the y yz plane. So x axis is perpendicular to both y, z and omega. Hence, there is no component of omega along the x coordinate system. I mean, in this definition, of course, this definition is for our convenience. There is no component of omega in the x direction, and hence only in the y and z direction, because omega lies on the y and z direction. So, sorry, omega lies in the y and z plane. That is the reason why we have only the y and z components of omega. So in terms of in component form, the term 2 omega cross u can be decomposed as, in the x direction, two omega cos phi times the vertical velocity minus 2 omega sin phi the y velocity. In y direction, the component of 2 omega cross u, we are writing now the components of 2 omega cross u. This is 2 omega sin phi u. In the z direction, minus 2 omega cos phi u. This is for you to verify by doing a cross product of omega and u, given that omega is this, omega lies on the yz plane, there is no component along the x direction, that is the I cap direction. Omega has a form. First of all, convince yourself from the geometry that omega has a form like this, and then once you are convinced, then do a cross product of omega cross u. You know how to do a cross product, u I j k, this omega x, omega y, omega z, u v w. Do a cross product of this, and then you will find that in the x direction the components are these, in the y direction the components are the next ones, and the z direction the components are these. So now, for convenience, we define again similarly how we had done it previously for a particle rotating on a plane or moving on a plane which is rotating, 2 omega sin phi. So this is what we define for a convenience, and this is called the Coriolis parameter. As I told you there, that we'll have a different form of the Coriolis parameter once we go to motion on a sphere. This is the form of the Coriolis parameter. Initially on a plane, it was just 2 omega. Now we have 2 omega sin phi, which phi is the latitude. So f is greater than 0 in northern hemisphere. F is less than 0 in the southern hemisphere, and f is 0 in the equator. So hence using this definition of f, these are the characteristics that will happen. These are the characteristics of f in this rotating earth, and using the definition of f, the unforced motion are given by du dt minus fv equal to 0, dv dt plus fu equal to 0. So this, of course, this set of equation is same as that what we had derived for equations in a what we had written down for equations in a equations of a particle on a plane. This has to be the case, but now here the definition of f has changed. F was just 2 omega in that case. Here it is 2 omega sine phi. This motion on a sphere. So this is, f has different values in the different hemispheres of the sphere in which it is rotating. So now this is, we have the same equation, and you will, of course, again we can do the same exercise. We find the general solution and we can get the radius of the trajectory, and because the trajectory itself will be circular motions. So this is everything is same except that the conclusion here is the motions so the inertial motions are circular with time period two pi over f. So this is same as the previous case. However, the definition of f is now 2 omega sine latitude. So now there's a question which might be of interest to you. Just try to find out the inertial time period at the poles and the equator of Earth. Get the inertial time period of, at the poles and the equator, and you will see how both of these are very contrasting, and this might be of interest to you as a homework problem.